Welcome back to another tutorial. Have you ever seen those ads when you have to fill in the colors of a pixel art by clicking on squares with numbers in them? Well, that is what we are going to make today. In this video, we'll go through the process of creating a color by number game. I do have to preface that this tutorial will be a little bit more complicated than usual, as I try to make this template dynamic for you to easily customize in design levels. Anyways, let's begin with the video. The first thing we are going to take care of is the camera. If you've ever played one of those games, you might have come across massive artworks that are way too big to fit within the screen. Therefore, it's imperative to implement a function that allows the player to move the camera around. Ideally, we would also want to have a zoom feature, but considering that this tutorial is already as complex as it is, it's probably best to leave it in favor of keeping our lives simple. We'll start this off by creating custom script blocks to determine the edges of the artwork. From here, we can use the getPosition block to save its position into a variable. If we go ahead and inspect this value, you can see that the block's position has a lot of decimals. That is because we are retrieving the position of the object's center of mass. However, we would want to instead get the position of the cubic space in which the block is contained, because spoiler alert, we'll be using a raycast to go through all of the blocks within this grid. To fix this issue, we would have to snap its position. We can achieve this by breaking this vector into its own coordinates, writing down all the values using the floor block, then compiling them back into a vector. If we inspect this value again, you can see that now, the values are all integers. But we're not yet done. If we quickly grab a block and inspect its position, notice how there's always a 0.5 at the end. And since we want to imitate the position of a standard block, we simply have to add an offset of 0.5 in all axes. Let's also attach it to a place sensor so that this only executes at the start. We will also create another block to represent the southwestern corner and duplicate the code to place it there. Of course, we also have to change the variable's name. And now we have our two edge coordinates. Next, let's make up a random assortment of blocks just as a frame of reference, because now we are going to move the camera, or at least initiate it. Let's start by using our position variables and taking the x and z coordinates. And the reason why we gave these values an offset is because we don't actually want to start from the block. For instance, in the northeastern coordinate, we would want to move one block left and one block down. Likewise, for the southwestern coordinate, we would want to move one block right and one block up. That way, this square fully encompasses the space that we have. Let's swiftly rename these to be the max values. Then we'll initialize the camera position to be at the center by adding the two vectors and scaling the result by 0.5. Let's also fix this typo as this has to be NE. Then for the camera distance, we'll fix it to be 30 for now. Afterwards, let's take our cam variables and plug it into a set camera block. Set the camera angle to 90 in the x-axis to get a full top-down view, and copy that value for the light rotation to get rid of shadows. We can now see our block situated at the center of the screen. We are now going to focus on setting up the lerps in our camera position and distance so that we can have some smooth tweens. This involves creating two more variables to act as our goal values, taking a field trip to the block section to find fan scripts, editing it so that it's a part of your project section, and looking for it in the inventory so that we can take the number and vector lerp. And from there, we'll create a lerp for our distance by having cam as our from input, CG as our to input, and the amount to be 0.125. We'll also do the same for our position. You may think that nothing has changed, but if we change the value of cam and set it to 0, note how the camera now zooms out. And that is the power of linear interpolation. The next thing we are going to implement is the controls for dragging the camera around the canvas. But before that, let's briefly talk about the logic on how we are going to go about this. Whenever the player begins to touch the screen, we'll fetch the coordinates of where the finger is and save it into a variable. While they are in contact with the screen, We'll get the current coordinates and compare it with a variable to determine the drag velocity. We'll then use this as an offset to move our camera around. I'm also going to provide you with some more information about the touch sensor. This block is responsible for registering touch input. It has 3 modes. Touching, wherein this executes as long as the player is touching the screen. Begins, wherein this executes the moment the player touches the screen. And ends, wherein this executes the moment the player stops touching the screen. Whenever a touch event is happening, it will output the x and y coordinates of where the player is touching, and these values go from 0 to whatever the device's dimensions are. We'll start by taking our screen size and finding the minimum and maximum values to be the device's x and y sizes. By doing this, these values will not change even if the player changes their screen orientation. Let's add an if condition so that we can disable the controls once the game is stopped, and then we'll bring out the touch sensor set to begins. It's also important to know that this goes left to right, top to bottom, so if I tap at where the pause button is, observe how our coordinates are low values. However, if I tap at the bottom right corner, these coordinates now have a huge jump in value. Also, notice how the max values are completely dependent on whatever the screen size is, and how this would pose a problem in setting up the controls. What would happen is that players with small devices would have to drag entirely across the screen to move, while players with large devices would have to drag just a tiny bit to produce the same amount of velocity. We can make this more consistent by dividing these coordinates by the device x and y sizes. That way, these values are now relative to the device's dimensions, going from 0 to 1. Next, let's create a vector out of these values and save it into the variable drag_old. We'll get another touch sensor, this time set to touching, and copy the same code. We'll save the vector into the variable drag. Afterwards, we can proceed with changing CG by using the difference between the drag positions as an offset. If we press play, the camera is moving, but it is totally drifting away from our grid. To solve this, we'll update the value of drag_old to the current value of drag to reset it. However, this movement still feels incredibly janky. The camera does not move along based on where you drag, especially on the diagonals. What we'll have to do is to rotate this vector by a rotation of 180 in the x-axis to orient it to the right direction. Let's also change the magnitude to speed it up. Now everything's fine, although we would want to set up some boundaries for our camera as we don't want our player to just free roam into nothingness. Let's break this vector and use the min and max blocks to clamp our camera position. We'll use the edge coordinates earlier to help us define a range. Once we press play, our player is now enclosed within the space. Next, we should start deciding the artwork for this level. You can go ahead and create color blocks for which each one has a specific ID, but not only is it such a hassle to carry out, it would also count towards a script limit because we have code inside the blocks, and this could be a problem if you're creating a large artwork. Instead, a clever approach is to make a bunch of number blocks varying in height to represent our colors. Make sure that they're unglued to avoid connecting to one another. Now we have 8 blocks, wherein each one is a voxel taller than the previous. It's also vital information that I created all of these layers using the box template, meaning that they all have a box collider. This will be useful once we start setting up the raycast to scan these blocks. Then, let's create a module to assign all of the colors for the canvas. It's all pretty straightforward. All we have to do is save the object into a global list, which is denoted by the $, and add an increment to the list length. Grab the pink plug and put it at the side of the script block to have an input wire, as well as the execute wires at the start and end of the code. Afterwards, this is the point where you start creating all of the color blocks you'll use for the pixel art and connect them to the modules. Although, I do advise to keep the number of colors small for the time being. To check if everything has worked out, you can inspect it if the list length matches with the number of colors you have, or you can play around with the blocks to ensure that they're in the list. Next, it's time to design the artwork. Use the numbered blocks and remember their corresponding colors. The next thing on our list is to build a level scanner to go through all of our blocks within the grid. I'm going to bring a block to demonstrate how this will go. Essentially, our raycast will start at this position and it will go up. If it doesn't detect anything, it will simply continue. If it does, however, like this block here, then the game will be able to see that this is the number 2 block, therefore it should have the number 2 color. We go up again and this time these cells are for color number 1. Once we reach the end, we go 1 block to the right and return to the bottom. This then goes on all throughout the grid until we stop at the top right corner. Let's begin with a place sensor to have this only run once. And then we'll place 2 loops, one for X and one for Z, wherein the loop length is taken from the difference between the edge coordinates. We'll also add an offset, for which I'll talk more about later. Using the X and Z counters, we can then determine the position on where we'd want the raycast to be. Our starting point will be the bottom left corner with some offset. Once we have the scan point, we can then plug this vector into a raycast to look for blocks below this position. As you can see, the red lines indicate that they detect something underneath, but some blocks remain unaffected. That is why we need to have the raycast to start from up high. Also, take note of what happens if we remove the offsets. The scanner starts inspecting spaces that include our edge coordinates, which is something that we don't really want. If we take a look at the raycast head position and inspect the Y coordinate, notice how they are all multiples of 0.125. If we divide this by 0.125 and round it, the value we get now reflects the numbers we see on the board, although we do have to subtract it by 1 to match up with our color list. Let's also hide objects once we've detected them, and now we have nothing. Great! Before we continue with working on the scanner, let's take a little bit of a detour. As of right now, it's pretty difficult to create artworks because all you see are numbers. You have to correlate yourself which colors they belong to, and it's such a pain. Wouldn't it be better if we have a mode where we can see the result with no numbers and fully colored? Let's start by placing a script block, editing it, and giving it a little bit of a design if you want. It's completely optional, and it's also important to have this execute before the main script. And inside this container, we'll have 2 things, a boolean named test and a true value. And so anytime that this block is present in the level, that variable will be true. Next, we don't want to activate our controls when we are in testing mode. So let's set up a boolean that becomes true if either test or stop is active. Then replace our if conditions with it. Now, we cannot move the camera anymore. If test is active, the game should create a copy of the block's corresponding color using the height as the index, and position it based on where the scan point is. We can now see the artwork, but it's currently way too zoomed in. To fix this, we just have to set the camera distance to be zoomed out by getting the distance between the 2 edge coordinates and scaling it. We now need to display the numbers to represent what color these tiles should have. So of course, we would have to make some blocks. But hold on, there is an obvious path where we have to create 8 different blocks to represent our numbers. Though the problem with that is that they will add up towards our custom block limit. Right now you shouldn't worry about that, but there is a way to make this process more compact. Since a block is 8 voxels high, what we can do is stack up all the numbers 1 to 8 and unglue them so that they won't attach to one another. That way, we can have 8 for the price of 1. So let's go ahead and do just that. Once you're done, click the gear icon and change the type to physics. This allows us to position them easier. Let's go back to the main script and assign all of these numbers into a list. Here's a tip when working with lists. If you attach the output from a list element to the variable of another list element, it adds up the indices. So for example, the third item of this list has the value 20. You can get the same value by either retrieving the third item of the list, or by having 2 list numbers with 2 and 1 as their indices, or maybe 3 list numbers with 1 being the index. We are going to use this trick to slightly optimize our code. Make sure that each layer of the block is attached by a pink arrow. Afterwards, let's start initializing our colors. For now, all we have to do is to check if this particular color is the white block. If so, we set the index to be the white's ID and set a boolean to true, telling the game that there is a white color. Let's also play some SFX to make sure it works. If there's a white block, we hear a chirp sound. And if we remove this, silence. Then, we'll have to test that truth variable. The reason why we are doing all of this is because at the start of the game, all of these pixels will be white. Normally the color index would be something like -1, but this system gets compromised in cases where white is a color in the artwork, as there would be 2 numbers pertaining to the same color, -1 and whatever ID the white block has. To fix this, we can check if there's a white color, and if there is, we specify that its ID should be the default color for all of the squares within the grid. However, if that's not the case, then we'll set another block to be white and assign the white index to be -1. Let's go back to the scanner. If the test mode isn't active, we create a copy of the white block, save it into a list, position it based on the scan point, and add an increment for the list length. Make sure to make this variable global, and everything seems to be fine. All of the number blocks are now white. A pixel would have 2 properties, the current color ID and the goal color ID. We'll set the current color to be white and the goal color to be the height, which if you remember, corresponds to the number block this pixel replaced. Next, let's create a copy of the number, save it into a list, and position it to be on top of the pixel. You can see the digits, but they disappear after a short amount of time. First, let's remove this SFX as we don't need it anymore. The reason why that happened is because we changed the type to physics, meaning all of these blocks were affected by gravity. Also, I would like to add that the numbers were placed directly at the center, despite the fact that it wasn't at the original block. Since it's a physical object, the center of mass is right at where the digit actually is, as opposed to being at the center of the cubic space. Anyways, we can use the setLock block to lock the number's position and rotation so that it becomes static. And that did the job. It's also useful to make use of comments to have an idea about what each chunk of code does. After that, let's talk about the controls. Right now, we need touch input to direct the camera on the canvas. However, we also need touch input to paint the cells. We don't want them to happen simultaneously, so what do? At the start of the touch, let's set the variable drag hold to 15 and CG hold to CG. Drag hold is the amount of frames before we can say that the player wants to color instead of move around, and CG hold is the initial value of the camera goal position. Let's detach this section for a second as we try to get the touch position, and for here, we will be using the screen to world block. This block is the opposite of the world to screen block. It takes the screen coordinates and outputs the start and end positions of a line going to that specific point. So if you ever tap anywhere within the screen, connecting these X and Y values to this block will give two positions. One that's very close to the camera and one that's very far away. We can use this block to get the touch position by converting the screen coordinates to world position and plugging it into a line versus plane block. Set the plane point and normal to 0.5 in the Y axis because that is the Y value of our pixels. To check if it works, we can get a block and set its position to where the touch is. And as you can see, it follows along where my finger is. Next, we'll set up an if condition that checks if drag hold is greater than 0. Basically, we want to move the camera as long as the player isn't holding their touch. We'll set up a truth variable that becomes true once there's a difference between CG hold and CG, so once this is true, drag becomes true, and since we have an OR block, this will always return true as long as one of the inputs is true. We do want to set it back to false at some point, so get another touch sensor, set the mode to ends, add an if condition for drag, which we won't do anything for right now, then change the value back to false. Let's inspect to see if all is well, and as expected, this boolean becomes true as soon as there is a change in the camera position, with it resetting back to false as we let go. And notice how it doesn't activate if we're just holding in place. Let's check if the boolean is false, and if it is, we decrease the value of drag hold. So now, what happens is that once we hold for a certain amount of frames, we can't move the camera anymore. Once we've held the touch for a while, we activate the mode that allows us to drag around and color nearby pixels. That means that we need to find the closest object. Set BID to -1, which is the index of the closest pixel, and best to 1, which is the distance from the closest pixel. Loop through all of the blocks. Check if the distance between the position and the touch position is less than the best value. If it is, then we update our values. At the end of the loop, check if BID is still -1. If it isn't, then that means our loop found an object close enough. Let's play around with the rotation to see if it works. Press play, and voila! The closest pixels to our touch spin. Next, let's check if the pixel's current color is equal to active, which would be the player's current color. We haven't done anything with it yet, so by default it should pertain to the first color you've added with a module. Let's play a plop sound effect with some randomness in the pitch to add variety, set the pixel's current color to the active one, get its position, delete it, clone the corresponding color block, update the list item, and place it to where the previous pixel was. So now we can drag around to dye the white cells to yellow. Now it's time to design the user interface for a game. But what exactly is a user interface? Well, it's the joystick, it's the jump button, it's the help bar, it's the pause button. It's essentially anything that's on the screen that either provides you information about the game or allows you to interact with a game. The keyword here is on the screen, because anything that you can see in the game is technically inside the screen. These UI elements, however, are situated on top of everything so that they don't affect anything. In our game, we would want to add buttons that allow us to switch colors. The idea is to have a small section of our colors to avoid overcrowding the screen, as well as navigational arrows to go through the rest of the palette. First, let's head back to the initialization section and create the digits that correspond to our colored blocks. Save them into a list. and lock the position and rotation. Next, let's create a big space because this is where things can get messy. Let's create a loop for the colors. Save the loop index to a variable, a vector variable for the position, and set the color's location based on that variable. Let's bring in a screen size block, a screen to world block, and a line versus plane block. We'll be positioning our colors by fiddling with the screen X and Y values. Let's set the height to 5 units high so that they don't interfere with anything. I'm also going to quickly fix this. Now, you can see something happening at the bottom right corner of the screen. Since we've plugged in the screen size with no changes, and the fact that it goes left to right, top to bottom, the max values of X and Y brings the colors to that corner. Then, if we multiply X by 0.5 and Y by 0.875, they now show up at the bottom middle. That is because we changed X to be the halfway point and Y to be slightly above the edge. We'll leave the Y value mostly unaffected, but we'll have to make some changes for the X value. We'll need two things when it comes to positioning them: the index and the amount of items within the list. We have 0.5 as the midpoint, and the gap between each color depends on the number of items. They would be far apart if there's only a few of them, but they'll squeeze in if there's many. Starting from the index, we'll subtract that value by the midpoint of the amount of items minus some offset of 0.5. That is a lot, let me explain. Say that there are 3 blocks. That means the midpoint would be 1.5. However, that is not going to actually work. Since list items always start from 0, that means 2 items will be at the left side, and that is not centered properly. That is why we subtract that value by 0.5 to become 1. The first item is 1 unit to the left, the second item is at the middle, and the third item is 1 unit to the right. We'll use a modulo for our loop index since we only want to show 3 at a time to avoid overcrowding. Then we'll multiply 3 by 0.5, which is the same as dividing by 2, and subtract by 0.5 to get 1. And when we press play, you can see that the colors are now positioned. The next part is completely optional. If you do want to skip it, then you can just play around with spacing until you have something that feels right. But basically, we want to center the colors based on how many are currently present, because right now our system only works if there are 3 items. If we ever switch and there are only 1 or 2 present, they will appear at the left side of the screen. Let me just quickly place all of these blocks and I'll explain the logic later. Basically, we have a min block so that the maximum amount of colors shown is 3. Next, we divide the index by 3, round down its value, then multiply it again by 3. That way, 0, 1, and 2 will give us 0 since the quotient from dividing them by 3 is less than 1, and flooring these values give us 0. 3, 4, and 5 will give us 1, 6, 7, and 8 will give us 2, and so on and so forth. We then subtract this to the list length. In my case, I have 5 colors, so the first set would have 3 items, while the second set would have 2 items. I then attached it to where CSLN and 3 originally were, and if we test this out, you can see white and blue properly positioned as well, despite them being in a separate set. For the Y coordinate, we would want to add a slight offset to the active color so we know which one is the current color. Again, I'm just going to add all of these blocks and explain later. First things first, we subtract the index from the active ID. If it's the same value, then we'll get 0. We then plug it to a divide block so it becomes 0 divided by some number. As we all know, 0 divided by 0 gives us an undefined value, and any other number gives us 0. We attached it to a min block, with the outer input being 1. So now, what happens is that if the index is the active ID, we're divided by 0, which gives us an undefined value, and since the min block is looking for the lesser value, it would get 1. However, if they have different values, this becomes 0 and min block gets 0. Finally, we'll multiply it to a negative number so that the active color goes upwards. The next thing we have to do is to only show the colors of the current set. Once again, allow me to place all of the code and do the explanation later. After all of that, we set the visibility of the color based on the truth variable and if we can also move around. Current tab represents the current set active. As I've said earlier, colors are divided into sets such that the first 3 items are the first set, the next 3 are the second, and so on. For the first condition, we add a 1 to the variable and multiply it by 3 before checking if it's greater than the index. So if current tab's value is 0, it becomes 1, then after multiplying it becomes 3. This condition then only becomes true for the first 3 colors, as anything after that would have an index greater than the value. However, this is not enough. Let's say current tab is now 1, and after adding and multiplying it becomes 6. This condition now becomes true for all of the 6 colors, which is a no-go because the max amount of colors shown is 3. That is where the second condition comes in. We multiply current tab by 3 and check if it's less than the... hold on, this is supposed to be a plus. Anyways, less than the index plus 1. The reason why we add by 1 is because of the fact that the index starts from 0. Going back to our issue earlier, if current tab is 1, then these 2 conditions together will only be true for colors 4 to 6. And if we test this, you can see that the white and blue are missing. Next, let's also display the colors' corresponding numbers. We'll just copy what we have and place it at the right side. This runs before that because of execution order. Next, we'll replace the object variable with a number and attach it back to the setVisible block. Increase the Y position so that it appears on top, and it seems like everything works. It's time to add the navigational arrows to switch between tabs. Create a block for the arrow and change the type to physics because again, we will be positioning these arrows, so it would be good to have the center of mass to be at the center. Let's add a loop that runs twice, which creates a copy of the arrow, saves it into a list, and locks its position and rotation. I'm going to clear up space for this chunk of code. We'll essentially just do the same thing that we did with the colors, and it's a whole lot simpler. The difference this time, for the x-coordinate, we either move it to the left side or the right. To do this, we subtract the index by 0.5, so it becomes either negative 0.5 or 0.5, and multiply it by 2 to get negative 1 or 1. We then scale it with the spacing. They're now positioned properly, but we do have to rotate them to the right direction. We'll make a rotation wherein the y value is the index multiplied by 180 minus 45. Afterwards, we have to set the visibility of the arrows. The left arrow should be visible as long as the current tab isn't 0, and the right arrow should be visible as long as the current tab is less than the total amount of tabs. To get the total, just divide the number of colors by 3 and round up the value. Then we can set the visibility to be that truth value and the inverse state of controls. We should also save that truth value into a list. Now the left arrow is hidden, while the right arrow remains unchanged. Let's get back to the controls. If the player stops touching the screen and they haven't dragged the camera, we'll loop through all of the colors and search for the closest one. We'll add an offset to the color's position so that they're at the same height as our touch position. This is 0.5, while this is 3, so 3 minus 2.5 is equal to 0.5. We'll also add in a truth variable earlier, so that it only checks the shown colors. At the end of the loop, if we find an object, we check if its index is equal to the active ID. If it isn't, then we play a beep sound effect and change the active color. Now we can switch between colors, and we can actually paint with any color other than yellow. If we don't find any object close enough, then we'll see if the player has pressed on the arrows. We'll set a truth variable to false, loop twice, and check if that variable is still false. If it is, then that must mean that they tried clicking on a pixel, so redirect it to that chunk of code. Now, we can actually color one by one without having to drag across. We'll duplicate the code earlier and change a couple of things. This becomes arrow and that becomes arrow. Readjust everything to make it look tidy. And if the player is pressing an arrow, we play some SFX and check the index. If it's 0, then it's the left arrow, so we decrease current tab by 1. Otherwise, it's the right arrow, so we increase by 1. Hi, I totally forgot to set the truth variable to true. Anyways, make sure to add it in your code to tell the game that the player is pressing an arrow, and therefore it shouldn't check if they've clicked on any pixels. Finally, it's time to implement the win condition as well as update the numbers for the pixels. We start with an if condition so that this only runs if the game hasn't stopped and if we aren't testing the canvas. We set the win variable to true and loop through all of the blocks. From here, we check if the block's current color is the same as its goal color. We then invert its value with a not operator to set our block's visibility. You can see that the white blocks don't show any digits because they already have the goal colors. If we paint the picture, you can see those numbers disappearing. However, it would help the player a lot if there was an indicator that tells them which pixels match with the active color. To do so, we'll check if the goal color is equal to the active ID. If it isn't, then we reset its rotation, otherwise we give it a little bit of a tilt. Now, numbers turn if the color corresponds to the active one. Then, we update the state of win by using an AND operator. That way, once the truth variable becomes false, then win will always be false because the operator requires both inputs to be true. If this variable is still true at the end of the loop, let's play some SFX and trigger the stop boolean. I'll just complete this picture. And as planned, we only hear a sound once because we've set the stop variable to true. Let's remove the chirp. Set the camera goal and distance so that the game shows the entire thing. And have a more appropriate SFX. Once the stop variable is true, let's set up a timer that runs for 30 frames before executing the win block. And now, hopefully, once I finish this pixel art, we get a nice look at the result. This marks the end of this tutorial. However, I do encourage you to use this template as a starting point and expand it with new features and functionalities. For example, this can only support up to 8 different colors. How about 9? How about 10? What if you set up a system to create digits without having to designate a block to each number? Right now, we're only rotating numbers if the goal color matches with the active one. What if you created a separate set of digits specifically for this issue? Can you implement a zoom function? Maybe you can utilize the camera's perspective mode and attach the UI elements to the camera position rather than relying on screen sizes. Those are just some ideas on how to improve the game. Nonetheless, I hope you learned a lot from following this tutorial. I also added a GitHub link in the description where I post the code screenshots, so you can take a look at those if you ever got stuck somewhere. Anyways, thank you for watching. I'll see you at the next one.